part of the lectures, Professor Harlow rather have all the questions during the lecture. So if you have any kind of question, even over and above the clarification ones, you can go on and ask. As always, you can book your spot by writing in the chat Q for a question or F for a follow-up, and I'll give you the word. This said, I'll leave the space to Professor Harlow, and you go.
All right, hi everyone. So I guess this is the last lecture, so thanks for coming to all the lectures, or at least to this one, since you're here. I tried to include a little bit less material this time, so hopefully there's some more time for discussion at the end, although we'll see what happens. Last time we learned the basics of ADS-CFT, our favorite theory of quantum gravity, or at least my favorite theory of quantum gravity. There's an obvious criticism, however, of the proposal that we need to consider. Okay, so obvious criticism, which is that d-dimensional QFT equals d plus 1 dimensional gravity. That's crazy. Okay, it sounds totally nuts, right? How can a quantum field theory that's local in d space-time dimensions pretend to be something that's local in d plus 1 space dimensions? That sounds hard. Wouldn't we notice? I don't feel confused about the number of dimensions that I'm living in, but if holography is correct, then actually the number of dimensions I'm living in is lower than I think. But then what's going on? Why am I so convinced that I'm living in 3 plus 1 dimensions? Okay, so that's the question that we're going to study today. Now, I can try to formalize that's crazy a little bit. That's crazy, I guess, well, especially for philosophers, but even for physicists, that's not a very formal criticism. So let's try to make it more mathematical. Okay, so here's our picture of ADS. And let's say we've got some time slice here in the center, and let's have some point little x here, and some point big X here, okay, which is a point on the boundary. Okay. And let's consider a bulk field, phi of little x, living here. And also, let's take a CFT local operator, big O of x, of big X, and put it there. Okay. So if we believe that the bulk theory in this picture is really 2 plus 1 dimensional. So in this example, the boundary is 1 plus 1 and the bulk is 2 plus 1. I draw that because that's what I can draw. Then bulk locality should suggest that the commutator of phi of little x with O of big X should be 0, because they're space-like separated, right? They're both living on the same Cauchy slice. Now, strictly speaking, in gravity, that's not quite true because there aren't local operators in gravity, so there's some correction to this at higher order in G, and there's a story about that, but we're just going to neglect that in this lecture. Okay, the conclusions are the same after you are more careful about that. So this commutator, right, would express the independence of what's going on in the center of the bulk from what's going on near the boundary. And we, as we discussed before, local operators in the boundary theory should be thought of as sort of limits of bulk things, right? So they should be thought of as living right near here. And so by bulk locality, you might expect that this should be true. Okay. On the other hand, from the boundary conformal field theory point of view, this is an extremely puzzling equation, because in QFT, there's something called time slice axiom. Which says that if phi of x commutes with all local operators on a time slice, I'll finish the sentence up here, then phi of x has to be proportional to the identity operator. Okay. So the intuition here is that in a quantum field theory, remember, we have this, we have this Hilbert space, which roughly speaking was the tensor product over all the points in space. Okay. So every operator is a sum of products of operators that just act on these single sites, so local operators. But then therefore, if you commute with all the local operators in a Hilbert space like this, then you commute with all the operators, because if you commute with all the local operators, then every operator is some sum of products of local operators at various points, and so you're going to have to commute with all of those too. And if you commute with all the operators on the Hilbert space, then there's something called Schur's lemma, which says that you have to be proportional to the identity. Okay, so it's called an axiom because we don't understand anything about quantum field theory rigorously, but to the extent that you're allowed to think about quantum field theory like this, then it's just a true property of quantum field theory. And this is rather puzzling, right? Because I can put any local operator I want here in the boundary conformal field theory, and they all, wherever I put it, they all look like they're going to be space-like separated from this point in the center. And so if I believe that this bulk locality is really true, that the theory really is local in d+1 dimensions, then, well, if I try to represent this phi of x operator in the dual CFT, which I can do using this isomorphism we discussed last time, then the representation of phi of x in the CFT has to commute with all these O's, but then this axiom just says that it has to be proportional to the identity. And that would really not be very much fun, right? Like, I mean, this could be us living here, right? It could be me. And I don't feel like I'm proportional to the identity. I don't feel like all my eigenvalues are equal. That's probably not enough structure for me to think coherent thoughts and so on. So somehow this has to not be true, okay? Okay. But then we now have to immediately address the question of, okay, if it isn't true, then why doesn't this lead to massive acausality, right? Like if an operator here doesn't commute with an operator there, then that means usually that there's a telephone, right? Like I can, by doing some measurement here, measuring this operator, I can affect the outcome of what you would have gotten by measuring this operator.
Daniel, we have a question from
okay.
Siddharth.
Yeah, go ahead.
Yeah, thanks. So just before you go on, I just wanted to make sure I got this argument. So, so both phi of x and O of x, at least in the bulk case, are both entirely defined in the ADS theory, right? They're not referring. You haven't used the dictionary yet.
Yeah, although I've used it a little bit because I said that O of x could be an arbitrary CFT operator. And strictly speaking, I haven't given you a bulk interpretation of an arbitrary CFT local operator. I've just told you about these low dimension primaries. But the high dimension ones have bulk interpretations too. They're just operators that create a black hole in the vicinity of the boundary here. Yeah, so you should think of this O as being some operator that can create a black hole here, but it's over here. It's not in the center. It creates the black hole over there.
But the black hole is in the ADS sector, right?
Yeah, so right. So that's kind of the ADS interpretation of an arbitrary local operator in the CFT.
Okay, so the commutation relation is really between the black hole and some field.
Yeah, it's like in general, I mean, so for some O's, it'll just be a field, right? So for the O's that are just the limit of a bulk field, that's just studying the commutator of the bulk fields. But this, what I'm saying here is a little bit stronger. I'm saying that also the field that creates a black hole here should commute with this operator over here, because even though it's creating a black hole, it's creating it far away.
And the claim is that there are, even in the ADS sector, there's a whole ring of black holes which the bulk field commutes with, and therefore it has to be proportional to the identity.
Right. Well, I mean, so from the bulk point of view, there's no contradiction though, because from the bulk point of view, you do have an independent degrees of freedom here and here.
Right.
So you would just say that, okay, fine. So it commutes with all the black holes here, but that's okay because it's space-like separated and there's more degrees of freedom here.
Right.
The puzzle is that in holography, we think that really the boundary degrees of freedom are all there are.
Mm-hmm.
So
I see. So the bulk field also has to show up on the ring somewhere, right? That's
yeah. So there has to be some representation of this bulk field purely in terms of the boundary degrees of freedom in the dual CFT.
Okay.
And then the problem is in the CFT representation, how to see that commutes with the operators which we interpret as being near the boundary. Okay.
Okay.
And what we learned from this argument is that it can't commute with them.
Okay. Thanks.
Yeah. And so this is an illustration of what I said earlier when I said that ADS CFT requires massive non-locality. It requires the commutator of the operator that creates this thing in the middle of the bulk with something near the boundary to not be zero, because this thing is just made out of stuff at the boundary. Okay, pretty crazy, right? So that's the crazy, okay? Any other questions about this? I'm gonna develop it further in a minute, but it's kind of a good place if there are other questions. Okay, so I can sharpen this paradox by introducing another new tool. So I apologize, this will be basically the last new tool I have to introduce for ADS CFT, but I'm not really going to explain too much about it, but we at least have to understand the basic idea. So I have to introduce something which is called ADS Rindler Reconstruction. So this is a claim that if R is a ball-shaped boundary region, and we are near the vacuum, then the following is true, and it's actually easier to just draw a picture rather than to try to write it out. So I'll draw the ADS3 picture. So this is a time slice of ADS3. So then the boundary is 1 + 1 dimensional. So then a spatial region that's a ball just means a connected interval. So this will be like R. Okay. So then last time we introduced this Ryu-Takunagi surface, gamma R. And so the claim is if X is a point that's on some slice between gamma R and R, so last time I called that slice H, okay? Maybe I'll shade it red. And let me also put another point over here. So then the idea is if X is in H, which is the red region, then phi of X, so any bulk field at this point, can be represented using only CFT fields in R. Okay, so this is some bulk operator, but I can pass it through the isomorphism and turn it into an operator in the CFT Hilbert space. And the claim is that if it's in between this RT surface gamma R, which was the geodesic connecting the endpoints, and R, the region here, then I can represent it only using CFT operators here. So I can give it a representation. It's an operator that only acts on those pieces of this tensor factorization, which are in R, okay, and does not act in the complement. And so, and that's also, so for Y, then that means Y can be represented in the complement, R bar. So like the rest, like say the rest of this is R bar, right? So Y is in between this geodesic and R bar. So then 5Y, so if I put 5Y here, right, then I can represent it in R bar. Whereas if this is, I put a 5X here, I won't write, it gets too busy, then I can represent it in R. And so the rough idea of this, the way you show this is that you you solve the equations of motion sideways using special features of the vacuum. Okay. So at first, so this is kind of a, it seems like a kind of limited statement, right? Because I had to assume the region was ball shaped. So in 1+1 dimensions, that's not much of a restriction, right? It just means it has to be a connected interval. But in higher dimensions, there are all sorts of regions you consider, and it's a bit weird to just consider ball shaped ones. And it's also, why should we only restrict to being near the vacuum? So I should just mention, so I mean, those restrictions came so that you could do this algorithm that I didn't explain of solving the equations of motion sideways. I see the question, Carol, just one sec. In fact, there's a conjecture, which is called the entanglement wedge reconstruction conjecture, which says that actually this works for any region R and any semi-classical state, not just the vacuum. So this algorithm doesn't establish this statement. It only gets you part of the way to gamma R in general. But actually, as I'll discuss at the end of the lecture, the stronger conjecture has also been proven. You just have to use fancier technology. So I'm just going to use the simpler one to make the arguments, since hopefully solving the equations of motion sideways doesn't sound too crazy. Okay, so now questions from Carol and then Eric, but Carol first.
So my first question relates to the geometry. So yesterday you have presented us with an ADS-CFT correspondence where the geometry is basically a cylinder.
Yeah. You may be frozen here, Carol. I'm not sure. Is he frozen to other people too?
Yeah. He froze.
Okay, why don't we go to Eric, and then when Carol rejoins us, we can try again.
Field theory lives on the cap and bottom of the state.
Sorry, Carol. Carol, we're having trouble hearing you. Can you start over, please? I think you're.
Sorry. Yes, I switched off the camera to have better connection.
Yeah.
So I start from the beginning. Yeah. Yesterday, you presented us with an ADS-CFT correspondence where the basic geometry is a cylinder, right? And the conformal field theory lives on the cap. And on the bottom of
Carol, do you mind? Why don't you try typing your question? Because I think, Carol, maybe try typing your question because your signal is breaking up a lot.
Yeah.
So while you're typing,
now, when you present with the ball-shaped.
Yeah, I think he also has a delay. Yeah, we can't hear you well, Kirill.
Okay, so Eric, why don't you ask your question in the meantime, and while Carol is typing?
Is this related in any way, or makes you or make use of Schlitter?
It's not completely unrelated because entanglement in the boundary theory is an important part of this story, as we'll soon see. But there's more to this than Schlitter, because Schlitter is just a statement about acting with an operator on the state to get another state. But this statement preserves the algebra of the operators, like the non-abelian algebra. So it's a stronger statement. I mean, also Schlitter is just a statement about quantum field theory. It's not a statement about the relationship, about a duality or something. But this is a statement about taking bulk operators and representing them in the boundary CFT. So it's a statement about the structure of the duality.
Okay, thanks.
Yeah. Other questions while we're waiting for Carol?
No, I don't see any. You can, I guess you can go on. And
so maybe we'll continue, and then just whenever he
yeah, I'll try to get in touch with him and get his question.
Okay, so the stated version of this, it looks a bit clunky with this restriction to ball-shaped regions and being near the vacuum, but there's this more general conjecture that drops those restrictions. And by now we're pretty convinced that the general conjecture is true. So whatever region you pick, everything in between the region and its, in general, quantum extremal surface or Rutaki-Nagy surface can be represented in the dual CFT just using operators in this region. Okay. So the reason I told you that is because I can use that to make this paradox of the radial commutator even more crazy. Okay. And even more crazy is good, I guess we agree, if we're trying to do paradoxes. For example, so say here's my bulk operator phi of x, little x, okay? And so we saw that we were going to get into trouble if we could show that it commutes with every local operator in the boundary. So let me now give you an argument that it really, really commutes with every local operator in the boundary. So here's the argument. So let's just pick a local operator in the boundary, this one, O of big X, okay? Well, I can pick a boundary region, say this one, such that its Rutaki-Nagy surface is like that. And so then this shaded red region is like that, okay? So then, let me give the region a name, R. So I can represent phi of x, I can represent it as an operator which lives only on R, okay? But you see, once I've done that, then that's the end of the story, right? Because if phi R is only supported on this region is space-like separated from O of x in the boundary CFT, okay? And we don't know much, even if you don't know much about quantum field theory, if you only know one thing, it should be that operators that have support at space-like separation are commuting operators, okay? And so this commutator really, really, really is zero, okay? No small corrections, no uncertainty, it's exactly zero. But then you see, okay, fine. What about this operator over here? Okay, this operator, now it's in the middle of the region, so maybe it doesn't commute with that operator. But you can say, no, ha, ha, ha. Now I'll just pick my region to be like this. So let's call this region R prime, okay? And then again, phi R prime, and let's call this one O prime, has to commute exactly with O of x prime by the locality of the boundary CFT. And so you see, for any local operator in the boundary, I can come up with a representation of this operator that definitely commutes with it. And Well, at least from the bulk point of view, this algorithm of solving the equations of motion, you can do it. I mean, it's the same operator. You're just solving them in different, representing it in different ways using the equations of motion. So you would guess that this phi r and this phi r prime are the same operator. But if they're really the same, if phi r equals phi r prime equals phi r double prime for whichever regions you can pick, then we're really in trouble with the time slice axiom, right? Because now we've really shown that the commutators are exactly 0, and then that'll tell us that this phi operator has to just be proportional to the identity. Okay.
Daniel, we have another question from Eric, and then I have Kirill's question wrote in the chat.
Okay, so let me answer Kirill first since he was waiting for a while. So let me read it. Okay, so actually, so yeah, in fact, so the restriction to ball-shaped regions is kind of, in some sense, because the ground state region, when you split it into a ball-shaped region and its complement, has exactly the same kind of representation. We didn't talk about, so in our discussion of Rindler, we split the plane in half, whereas here the boundary is a sphere, and we're splitting it kind of into say all the points above some latitude and all the points below some latitude, okay? But actually for a conformal field theory on a sphere, the ground state, when you split it into regions like that, has the same kind of decomposition. More practically, it's because there's a lot of symmetry in ball-shaped regions that makes it allows you to do separation of variables when you solve the equations sideways. But I mean, that's clearly not something you want to sort of general understanding of the correspondence to rely on. You don't want it to rely on spherical symmetry. And so that's why I mentioned this stronger conjecture of the entanglement wedge reconstruction, which actually can be proven using some of the techniques I'm going to talk about later in the talk. Yeah. Maybe I should also emphasize that the geometry of this region is different from the geometry of the spacetime in the bulk. The geometry of this region is a statement about the questions we ask about the theory, but it's not a statement about what's dynamically going on, right? There's some bulk metric geometry here that's doing whatever it's doing. And then we're just kind of choosing to query it, saying, what can we learn about it, only measuring things in this region? So it's a restriction on our set of observables. It's not like modifying the state of the theory or something. Okay, Eric, do you want to ask your question?
Yeah, so these two different representations, the one you get from using R and the one you get from R prime, are they unitarily equivalent?
Well, yeah, so if we were doing bulk quantum field theory, they would be exactly equivalent. They would be related by what's called a Bogolubov transformation.
Right.
So at least within the regime of validity of the semi-classical description, they're exactly equivalent. Now, in practice, they're probably not exactly equivalent. There may be some small errors and so on. And I mean, in the end, I'm gonna have to tell you that they're not exactly equivalent, because otherwise we'd really have a problem here.
But then if they're not exactly equivalent, then then it's not the case that there's a single representation in which phi commutes with everything. It's that you have to, so
well, I know that's right. So that's how we're going to have to get out of it, right? The way, I mean, so clearly the resolution of this puzzle is not going to be that phi is proportional to the identity. Okay, that's probably not surprising. That would be a very boring ADS CFT correspondence. And so the only other possible resolution is that these two aren't really the same. Right? Okay. And so that's where we're going to have to go.
Okay.
But then we have to understand why bulk effective field theory thinks they're the same. Okay, so let me describe one other. So there's one just to kind of emphasize a little bit more how crazy this this situation is. So this is the picture I'm contractually obliged to draw in every talk that I give, and have been for years. We can split the boundary into 3 regions: R1, R2, and R3, and we can have our operator phi of x sitting in the center here. So now this operator has the funny property that it's not it's not accessible to this Rindler reconstruction for any one of these regions, right? So this red region that we can reconstruct is like this for each of the three regions. Right? But on the other hand, if I take the union of any two of the regions, then this operator is in the wedge. Okay, like if I take R1 union R2, then now this is the right geodesic. And so this one does lie in between this geodesic and the union of R1 and R2. Okay, so this picture tells us that there does not exist a phi R1, a phi R2, or a phi R3, but there does exist a phi R1, R2, a phi R2, R3, and a phi R3, R1. Okay. Which is kind of crazy, right? I mean, so somehow the information about what's going on with this field is not very well localized in the boundary CFT, right? I mean, it's, where is it, right? It's not in 1, and it's not in 2, and it's not in 3. But it's in the union of 1, 2, or the union of 2, 3, or the union of 1, 3. And that's really very puzzling from the point of view of quantum field theory, right? Usually in quantum field theory, operators have the decency to know what their spatial support is. You know, we aren't confused about whether an operator in quantum field theory lives here or it lives there, right? Usually that's unambiguous property of the operator. Whereas here, somehow this ability to do these Bogolubov transformations in the bulk has suggested this kind of extraordinary redundancy in how we can represent bulk operators in the boundary CFT. So, okay, so that's it for the puzzles. I'll get into trying to resolve them in a sec, but I'm happy to take more questions about the puzzles first. All right, Siddharth has a question.
Yeah.
Yeah, maybe you're going to talk about this, but I mean, I'm just trying to remember. I'm blanking right now, but there's, even in ordinary quantum field theory, we have an argument that leads up to the claim that we can represent there being like fields localized to space-time, right? Anyway, I'm just trying to think about what exactly in that argument breaks down, because I feel like,
I mean, this phenomenon has no analog in quantum field theory by itself. Mm-hmm. Because in quantum field theory, we usually say that for any operator on the Hilbert space, its spatial support is unambiguous. Right. You know, you can define it by just looking at what the operator doesn't commute with, right? So you say you take the full set of local operators, and then you say the set of the support of you say you have some operator O, and then you define its support by saying it's the set of all points where at that point there's some local operator that doesn't commute with O. That's the standard way of defining ambiguously the support of an operator in quantum field theory.
Eric suggests some theorems. Maybe, I don't know. I'm just like, yeah. Maybe I'm just.
But yeah, particles are confusing. That's why we're talking about fields. Yeah. If you try to think about particles, then quantum field theories don't always have particles. But they always have fields. So that's why it's better to think about locality in terms of the commutators of the fields than in terms of what the particles are doing.
I guess I'm thinking of something like, you start with the Fock space, and then there's like this, maybe it's the GNS construction or something like that, that eventually gets you to localized. Anyway, I'll stop.
And you could be thinking about the Riesz-Leiter theorem that Eric asked about before. I'm not sure, but the Riesz-Leiter theorem. So the Riesz-Leiter theorem says that any state in the Hilbert space can be reached by acting with an operator in any region, that you pick. But that's different than this, right? Because that's a statement about what you get by acting on the vacuum. It's a statement about states. It doesn't mean that there's any confusion about where the support of that operator is. Okay. So we're clearly going to have to resolve all these puzzles. We're not going to resolve them by saying that ADS-CFT doesn't make sense, although I've encountered people who want to resolve them that way. In order to resolve them and still have ADS-CFT make sense, we're going to have to realize that we asked for something that was too strong. Okay. And so the way out that we're going to explore is that these commutators hold only in a subspace of the full theory. Okay, and the motivation for that is that you have to realize that for most of the states of the dual CFT, they don't look like this, right? As we discussed last time, most of the states have some huge black hole that's eaten up that part of the space. Okay, there's some black hole like this. Okay. And so maybe we shouldn't be so quick to try to make assumptions about what the commutators of these operators look like in states like this, because I mean, who knows if this operator even makes sense in a state like this. For one thing, we have to deal with defining it relationally to make sure that it's diff invariant. But even after we've done that, when its relational definition puts it very far behind the horizon of some black hole, you know, who knows, right? I mean, maybe we should be less careful. Maybe we should be more careful about assuming that we know what its commutators should be with things that are near the boundary. Okay. It's not obvious that this helps, although at least it makes it clear that more work is needed if this is all you ask for. But then you run into questions like, okay, you know, how big does the subspace have to be? How, you know, in the subspace where you do want things to work, how accurately can it work, and things like that, right? I mean, so as soon as you accept something like this, right, you're basically accepting the idea that space-time is emergent. Because you're accepting that something which in quantum field theory was fundamental, which was the encoding of causality in the vanishing of commutators of operators, is not going to be an exact notion in holography. So for the rest of the lecture, I'm going to try to develop this idea more mathematically, mostly in the context of an example where you can a simple example where you can kind of see how things are working. And then I'll just kind of assert at the end that this example sort of correctly is capturing what happens in the real deal. To proceed further, I need to introduce this idea of quantum error correction. So for us, quantum error correction will just be some mathematics, which turns out to be the right mathematics for answering questions like, you know, how small can you make this commutator if you only want it to be true in a subspace? Okay, so questions that we care about from the gravity point of view. But I should say a little bit about, you know, what quantum error correction is and where it comes from. Okay, so the basic idea is that quantum error correction was invented to protect the memory of a quantum computer from decoherence, which is induced by interactions with the environment. So when you're trying to build a quantum computer, that's like the number one problem, right? The reason why we still don't have quantum computers is because it's just very hard to preserve the coherence of a many-body quantum system for a long period of time. You know, you're trying to preserve the phases in the wave function, and you know, if you have 50 qubits in the state 0, 0, 0, 0, 0, you know, plus 1, 1, 1, 1, 1, then if you do a phase rotation of even one of the qubits, then it blows up the coherence of the whole state, right? Just like if you send 1 to -1, you know, on any of them, right? Then you flip that state from being 0, 0, 0, 0 plus to 0, 0, 0 minus 1. Any kind of error correction, quantum or classical. So error correction, the idea of error correction is always to protect the information using redundancy. So say that I'm communicating, for example, like with the Voyager satellite, which is very far away, and it's hard for me to, you know, when I send a, well, I don't, but when whoever does sends a signal, right, it's a very faint signal. It can scatter off of things along the way. So if I want to send a bit, a 0 or 1 to the Voyager satellite, the obvious thing to do is that I send the bit 100 times. Okay, and then, you know, some of the times the bit might get flipped or it might get lost or whatever. But then when the Voyager satellite receives my 100 bits or 90 bits or however many make it through, then it can just do majority vote. Okay, so maybe some of my zeros got flipped to ones, but as long as not too many of them got flipped, if Voyager does majority vote, then it'll be pretty sure that I was trying to send a 0, you know, unless the error probability is greater than 50%, in which case I'm just dead. Okay, then I need to find a new way of communicating. But you see, if the error probability is 25%, right, then if I only send the bit once, then there's a 25% chance I make an error. But so hopefully you all understand probability enough to know that if I send it 100 times, then the probability that with a 25% chance each time, right, then I sort of win exponentially in terms of, you know, the error probability goes like, 25% to the 100, basically, that the majority vote algorithm is going to fail. So you win pretty fast. So that's called the repetition code. So that's a code that's called the repetition code. It's the obvious quantum error correction code, right? And, you know, I have one bit and I just send it a bunch of times. Okay. Now, unfortunately, the repetition code does not work for quantum information. Does anyone want to type in the chat why you can't do the repetition code for quantum information? Anyone have a guess? Yes, Manus knows the answer. Yes, that's right, Enrico, very good. Yes. Yes, it's because we can't clone quantum information. So if I just have some state psi, yes, and I want to send it to you, right? I have to do the repetition code. I have to be able to make copies of the state, but I can't make copies of the state in quantum mechanics. So we have to come up with something else. And actually, this was like, for a while, like people thought that we would never be able to have quantum computers because of this, right? Like there was some lore that, you know, error correction won't work for quantum computers because of the no cloning theorem. But in fact, it does. There is a thing that you can do. And so the famous quote from John Preskill is that you use entanglement to fight entanglement. So, and to say it more carefully, so you encode quantum information non-locally in the entanglement between many degrees of freedom. So if I want to send you a state of a qubit, rather than just sending you a qubit, I send you, 10 qubits. But then the 10 qubits are entangled in some complicated way where the information that I want to send is encoded not, say, in the first or the second or the third qubit, but instead in the way that the qubits are entangled with each other. Okay. And that turns out to somehow be enough. That's a close enough analog of the repetition code that it enables error correction. So it's a kind of quantum redundancy. So you can, in some hand-wavy vague sense, you can kind of think of the entanglement as kind of like redundancy, right? Like, if you have your two entangled pairs, right, and you measure this one, whatever you get here, you're also going to get when you measure that one, right? And so that's some kind of redundancy. Now, that maybe sounds kind of vague and confusing. So to really convince you how this works, the obvious thing to do is to go through an example, which will hopefully make it clear that this is going to work. Maybe I'll ask if there are any quite general questions before we do the example, though. Okay, so the example I'll consider is called the 3-qubit code. Okay, so the idea is that I have, so a qubit is like a qubit, except it has 3 states. So instead of being 0 or 1, it can be 0, 1, or 2. So a state of a qubit looks like this. So some I from 0 to 2, I. So what the 3-qubit code does is it encodes one logical qubit into 3 physical qubits. Okay. And the way it works is like this. So I take my state of 1 qubit, and then I use my quantum computer to map it into a state that looks almost the same, except for this I tilde is a basis of a 3-dimensional subspace in the 27-dimensional Hilbert space of 3 qubits. And let me tell you what the basis is. So 0 tilde looks like this. 1 tilde looks like this. And 2 tilde looks like this. So if you think for a sec, you can see that that these 3 states are mutually orthogonal. Okay. So they span a 3-dimensional subspace of the full Hilbert, the full 27-dimensional Hilbert space of 3 qubits. Moreover, this subspace is symmetric under cyclic permutations. Right, so each of these states is invariant if I permute with qubits, right? And also each state is quite entangled. Okay. But why did I pick this subspace? Okay. Instead of something else, right? So why is it a good idea to encode the qubit this way? So to understand that, we need to make an observation. Which is that there exists a unitary transformation U12 acting on the first two qubits only and not on the third qubit. And also a state chi23, so a state that just a pure state living in the Hilbert space of the second and the third qubits, such that these encoded states look like U12 acting on, I just feed I into the first qubit, and then I feed this state chi23 into the second and third qubits. So this chi is just the maximally entangled state on two qubits. Okay, and then this U12 is a little bit annoying to write, but what it does is it sends 0, 0 to 0, 0, 0, 1 to 1, 1, 0, 2 to 2, 2, and so on. And so I write what it does for a complete basis in the notes that you can look at later. Is some unitary transformation on two qubits. And so in particular, this shows that given a logical state, psi, like say this one, some state of a single qubit, right? Then we can write the encoded version of psi as U12, acting on the tensor product of that state inserted into the first qubit, together with this chi state on the second and third. And moreover, by the cyclic symmetry, there also exists a U23 and a U31, such that we have also psi tilde, the same psi tilde is equal to U23 acting on psi 2 chi 3, 1, and also psi tilde equals U31 acting on psi 3 chi 1, 2. Okay. So we can just kind of permute the qubits around, so we can pick which two of the qubits this unitary acts on. All right, so still that's just mathematics. So what? Okay, we found these unitaries. Who cares? Well, here's why we care. So say that you guys are all in Italy, although that's not true, I guess, but some of you are in Italy. And I've got my qubit here in Cambridge. Say I've got a spin 1 atom. So that's a 3-state system, and it's living in some quantum state. And I want to send it to you in Italy. So, well, I could just put my atom in an envelope and send it in the mail, and the envelope would have to have a pretty good, refrigerator and ion trap and whatever. Okay, but let's assume that it has all that, and I can send it to you in the mail. But especially these days, with COVID, there aren't so many flights, and flying to Italy especially is always challenging. And maybe the envelope might fall out of the plane, or it might get lost in the airport, or who knows what. Okay, so what I do instead is I take my qubit and I encode it into 3 qubits. So I use my quantum computer here in Cambridge to instead prepare this state, which, if you like, is a state of 3 spin 1 atoms. I put each atom in its own envelope, and I send all 3 envelopes separately to you on different airplanes at different times. Okay. Now, of course, if they all get to you, then that was a waste of effort, and you can just take your quantum computer and you can transform back to the state that we had. But the real question is, what if one of the envelopes gets lost? Okay, so let's say, in particular, let's say that the 3rd envelope gets lost. It disappears somewhere in customs or something, which I'm sure has never happened in an Italian airport. Happens in our airports too, of course. So then that's okay, right? So say the 3rd qubit gets lost. Okay, fine. So you've got this state, but that's okay. You've just got the first 2 qubits and not the 3rd. So the state, since you don't have the 3rd qubit, you can just you trace out over it since you don't have it, right? But that's okay. Then you just conjugate by U12 dagger, U12. So you can do that because you did get the first 2 envelopes. And then, well, what do you have after you do that? Well, what you have is psi on the first qubit, tensor the identity over 3 on the second qubit. And hey, look, there's the state. Okay. So even though the 3rd qubit was lost, it doesn't matter. You can still just get this state in your lab. You can act on it with U12 dagger, and you've got the state back psi right there. Okay. And moreover, by symmetry, if instead of it was the 3rd qubit that was lost in the baggage claim, it was the 1st or the 2nd qubit, that's fine. As long as you know which one was lost, which, so say I read the numbers on the envelopes, right? Then say the 2nd one is the one that's lost, that's okay. Then you just use U31, right? Or if it was the first one that was lost, then you use U23. And so in this way, we see that the information is protected against the loss of any one qubit, right? So in particular, like if the probability of losing a qubit is P, right? So if I just send you the qubit in the mail, then the failure probability is P, okay? But if I send you these 3 qubits in the mail, right, then the failure probability is P squared, which is smaller, okay? Because you have to lose 2 of them in order to have a problem. So then you win by using the code. So hopefully this now convinces you that it's at least possible to do this thing of encoding the information non-locally in the entanglement between the qubits in such a way that it's protected against errors that affect small numbers of them. And this is an example, but this is a very general phenomenon, and there are theorems characterizing when it works and when it doesn't, and there are large families of examples, and so on. So let me stop and ask if there are questions. Everyone is happy with the 3 qubit code. if you want a fun homework problem, instead of looking up the unitary, see if you can figure it out for yourself. You know these states and you know this state chi, so you can figure out for yourself the U12 that such that this is true. Okay. So this should be already maybe somewhat reminiscent of this thing we encountered in ADS-CFT, right? Where we had this operator in the center of the bulk and we could represent it on any two of the boundary regions. But it's not, it's already kind of smelling like that, okay? And we can make it smell even more like that by introducing the notion of logical operators. So let me talk about that, logical operators. Right, because what we just talked about was recovering states, whereas there we were talking about recovering operators. So now let's talk about recovering operators. So a logical operator is just any operator that acts on the Hilbert space of a single qubit, right? So you know, it acts with some matrix elements like that. Okay. And well, so for any such operator, we can clearly come up with some operator O tilde, which acts on the encoded states with the same matrix elements. Okay. And I'll demand also that the dagger of it does that as well. So this O tilde is called an encoded logical operator. It's an operator acting on the whole Hilbert space of the three qubits, but which acting on the encoded states just implements the same transformation as this unencoded logical operator would have done on the original qubit. Now, in general, if we just pick this subspace in some arbitrary way, this operator O tilde will need to have support on all three of the qubits, right? If we just pick some arbitrary three-dimensional subspace and we write down an operator that acts with these matrix elements in that subspace, there's no reason why it shouldn't have support on all three of the qubits. Okay? I mean, why shouldn't it, right? You know, a priori, this subspace doesn't care at all about the tensor factorization into the three physical qubits. But because we've chosen our subspace intelligently, that's actually not true here. So in particular, I can define an operator O12 in the following way. I first act with U12 dagger to decode the state, okay? Then I act with my operator, whatever operator it is that I'm interested in, just on the first qubit, while the state psi is just sitting right here on the first qubit. And then after I do that, I just re-encode by acting with U12 again, okay? And so you can see basically immediately that O12 acting on any encoded state will act just like this O tilde. So it'll be a good O tilde operator. And similarly, its dagger will act just as O tilde dagger did. Okay. And moreover, bicyclic symmetry, there's also going to be an O23 and an O31. So I can represent the logical operator on any two of the physical qubits, whichever two you want. So this is really getting quite close now to what we had for this puzzle in ADS-CFT, right? We had this operator in the center that we couldn't represent on any one of them, but we could represent on any two. And here it's also kind of clear that we're not going to be able to represent this on any one of them, because because the reduced state on any one of these qubits is just maximally mixed, right? Like, so for example, on the third qubit, we can compute the reduced state, so then we can ignore the U12, and then we've just got half of this chi. So we just get the identity matrix. So clearly one qubit, any one qubit will not have enough information to learn about this operator, but we see that any two of them will. So, okay, now the moment of truth. So let's try to make this, so let's try to turn this into a theory of quantum gravity. Okay. So, so let's do qubit holography. So I'm now going to reinterpret everything that we just discussed in the language of quantum gravity. Okay. So let me draw the picture. So the three physical qubits we're going to interpret as local CFT degrees of freedom. Okay, and so here they are. Here's 1, here's 2, here's 3. Our one logical qubit we're going to interpret as local bulk effective field theory degree of freedom. And I'm going to put it here. So then we can draw these geodesics that we had before. Let me draw them again. Okay. And then what we learned is that with this interpretation, this ADS Rindler reconstruction story that I was telling you in ADS CFT is happening in this model. So this bulk operator, these logical operators, we view as operators that act at this point in the bulk. So this is a very kind of trivial bulk theory. It's a lattice theory with only one site sitting in the center of the space. We see that it's holographically encoded into a dual CFT, which is these three physical qubits, which are sitting at the boundary. Moreover, we can now directly see how radial locality works. So let's look, so let psi tilde and phi tilde be two states in the code subspace. So the code subspace, I guess I've been using that word, it's the subspace that's spanned by these three states. So let these be any states in the code subspace. And then let's look at the commutator of a logical operator, say with any operator on the third qubit. Okay, so this is exactly testing this. So any logical operator here, we interpret as a bulk field at this point, and then we take an arbitrary boundary operator at this point. So this is like the commutator we started the lecture with. This O tilde here is what I called phi of little x, and this x3 here is what I called O of big X before. Okay. So now we can compute this commutator. So O tilde is always acting to the left or to the right on a state in a code subspace. And so by these equations up here, I can replace it with O12. So this is equal to psi tilde of O12. Right. But then this is just zero identically because O12 only acts on these qubits. And X3 only acts on this one, and so they're commuting operators. Okay. And moreover, we could have played the same game, right? Like we could have asked about, what about, phi tilde, O tilde, say with X2, an arbitrary local operator on the second qubit. And then, hey, guess what? We can now we can replace it by O31. Oh, I wrote two. This should be a psi. and this should be of psi. And guess what? We get 0. Okay. And so you see that we indeed have that this commutator is exactly vanishing in the code subspace. This commutator for radio locality, despite the fact that in the end, this O tilde operator is being built out of the local operators acting on 1, 2, and 3. Now, one sec, Eric. And now I emphasize, right, I mean, this isn't a logical contradiction, right? The way I avoided the contradiction is that I only showed that this commutator has 0 matrix elements between code states. I didn't show that it was 0 as an operator. Had I shown that, I would have run into a contradiction with the time slice axiom, which here is not an axiom, it's just a true fact about 3 qubits. So, okay, Eric, go ahead.
So I mean, this is just really elegant and it's extremely cool. But there's a sense in which it seems like one of the central ideas of holography is getting kind of elided, because even though strictly speaking, the dimensions of 1, 2, and 3 are less than the dimension of the point in the middle in the bulk. Since you're effectively always using sums of direct products of these elements, you're kind of in order to represent things in the bulk, you really haven't reduced the dimension of your representation.
Well, in some sense, I have, though, right? So what I've shown you is that you can have an operator that behaves as if it's independent of all the local operators on the boundary. And so that's kind of the hallmark of having another dimension, right? Is that you have some knob you can turn on the operator, where as you turn that knob, it looks, for each value of that knob, the operators look independent. That's kind of what a dimension means from the Hilbert space point of view. Now here the knob is a rather discrete knob. It's kind of on or off. But that's kind of just because this model is oversimplified. I mean, so there are more complicated models where the knob has more settings than on and off.
Okay, I'm gonna have to think about this more. Thank you.
Yeah. So of course there is one thing that you can complain about, which I already hinted at, but let me now just discuss it some more. So an accusation you can immediately throw at me here is you can say, Daniel, yesterday you told us that ADS-CFT was an isomorphism. You said that every boundary state had a bulk interpretation, every bulk state had a boundary interpretation. And now you're talking about a subspace. So, okay, you told us that this 3-dimensional subspace has a bulk interpretation. But what about the rest of the states, right? I mean, it's not a duality unless you tell us what's going on also in the orthogonal complement of the code subspace. Okay. And so that's fair enough. I have to answer that question. Okay. So let's talk for a sec about H-code. H-code orthogonal complement. Okay. So here's the picture. Very simple. All right, there's a black hole and our point is gone. Okay, that's the picture. And this is a black hole which has 24 microstates, because the total Hilbert space is 27-dimensional. A 3-dimensional subspace of that we're interpreting as the states where this black hole is not present, and then there's that bulk field in the center. In the rest of the Hilbert space, this is what's going on. Okay. Now, in this model, this may seem a bit arbitrary. I mean, it's only 27-dimensional. So, this black hole is not going to have all the features of real black holes. But you can develop these ideas further, beyond this model. And you can see that this really is the right interpretation. So, if I had, 3 more lectures, then I would explain to you that in quantum error correction, there are rather general theorems which quantify like how big the code subspace can be, and still protect the message. I mean, clearly there's somehow in quantum error correction, the more redundant you are, the better protection you have, right? So if you have a lot of physical qubits and only a few logical qubits, then you're going to have better protection in general. Whereas if you try to have too many logical qubits for a fixed number of physical qubits, then the protection is going to break down. So there are theorems that quantify that trade-off. And you can use those theorems to study in ADS CFT, right? You can say, okay, so you come to me and you claim to be you're a CFT in D dimensions, and you come to me and you say, hey, I'm really a quantum gravity theory in D+1 dimensions. And I say, no, you're not. That's ridiculous. Okay. And then the CFT says, okay, try me. All right. So we start computing commutators, and we start in the vacuum, and then we start adding more states and computing commutators, and hey, what do you know? It keeps looking like it's local in D+1 dimensions, right? And I'm saying, okay, this is ridiculous. Okay, but I'm going to get you because I have this quantum error correction theorem that tells me that you can't fake radial locality for a subspace that's bigger than something. Okay, and so you say, okay, I'm going to be in a subspace that's big, and then you're going to have to admit that you're really just a d-dimensional quantum field theory. You're not local in D+1 dimensions, right? But right when you get to the point where that theorem is going to tell you that you break down from that you can't have the radial direction anymore, right? That's exactly from the bulk point of view where you expected this black hole to start forming. Okay. In my TOSI lectures, which I think were sent out in the beginning of the school, the mathematics of that is explained. So it should be actually readable to you guys based on what we've discussed. I just don't have time to explain it today. And so that really kind of brings it back to this initial discussion we had in the first lecture, right? Which is that in quantum gravity, you can have some kind of emergent and approximate locality for a while. But if you push things too hard, you try to probe that locality too precisely in too many states, then you're going to get hit by gravitational collapse. And now we can kind of see that happening in this model, right? Like you can try to make the code subspace if you make it even a little bit bigger. So in fact, this 3-qubit code saturates the bound of this theorem I mentioned. So if you try to protect even one more state in the bulk, then you lose the redundancy of the code. It stops working. And so it's really, so this black hole really comes in at sort of the last possible point where it could come in. One sec, Siddharth. So I mean, this I feel like even though this model is kind of trivial, it's also sort of very useful in sort of illustrating this sort of emergence of space-time from entanglement in a sort of the simplest possible setting. There are more complicated models that are somewhere in between this and full ADS CFT, which are based on tensor networks, and you can read about that also in the TOSI lectures of mine from a few years ago. Basically, there instead of having one lattice site in the bulk, you have a whole space-time's worth of lattice sites, and so it looks you can see it looks more like ADS CFT, but everything the basic way it works is all the same as in this model. So I was going to talk next about so that we're going to see in a sec that this Rutakinagi or quantum extremal surface formula we talked about last time also actually appears in this model. So that was the next thing I was going to explain. But first, let me stop and ask for questions. So I think Eric, I think, do you have another? That's your question, Eric? Yeah. So then Siddharth and then Vincenzo.
Yeah. So I guess I'm a little bit confused how this avoided the. So in the ADS Rindler reconstruction that you gave,
yeah,
you said that the bulk field can be represented only using fields in R, right?
Yeah.
But here you're using it looks like you're using everything, not just R.
No, that's this. No, this 012, 023, and 031 are like that, right?
Oh, right. Okay.
Yeah.
Okay.
So 012 represents it only on these two regions.
Right. Okay. Yeah. No, that makes sense. Right.
Yeah. Vincenzo. Yeah, that's a good question, Vincenzo. So one issue is that the firewall paradox has not been resolved yet. So I can't say that it's exactly the same. On the other hand, the reason why I invented this, years ago now, this paradox, was that I thought it was kind of a baby version of the firewall paradox. So the firewall paradoxes are in some sense algebraic. They arise from taking the local structure of effective field theory very seriously in the black hole background. And so the idea here was that this is kind of a simpler paradox that arises even in the vacuum. Where if you take the bulk picture of the space-time 100% seriously, you get to something that looks impossible in the microscopic theory. But then if you step back a little bit and ask only for what you need instead of what you might want, then you find that actually there's no contradiction. And so I think that this basic mechanism does also underlie the resolution of at least the version of the firewall paradox that I presented last time, because it shows how something can look independent without actually being independent. And the resolution of the firewall paradox, like the key thing was that we wanted this interior mode behind the horizon to not be independent from the Hawking radiation that had already come out of the black hole, but in some way that still respected causality. And here we see we kind of have a model for that, right? So yeah, and that's the kind of sense in which
so this is a toy model of a possible solution of the firewall paradox.
That's right. Yeah. And I would say this really is what happens for this paradox that I phrased today for the bulk, and for near the vacuum where you have this thing in the center and you want it to commute. And morally, I think it's also what happens for the firewall. That's becoming more and more clear every day. But yeah, I wouldn't say all the I's have been dotted and the T's crossed yet. Because the thing you need is massive non-locality that is consistent with the parent locality, and that's what I'm giving you here. Okay, so once it's clear that it's possible, then it's somehow you just have to figure out the details of how it works.
Sorry, can I follow up on that?
Yeah.
But the non-locality that was required for the firewall, or to get around the firewall paradox, was different, right? Because, well, at least there it was you were identifying regions in the interior with regions far away in the exterior.
Yeah. So roughly speaking, the way you have to think about it is that you have so at late times you have the black hole system and you have the radiation. And the way you have to think about it is that the black hole and the radiation are like these physical Q-traits, and the interior is like the logical Q-trait. So it somehow, the interior emerges from the shared entanglement between the black hole and the radiation. The key thing is that it's not just part of the black hole. That was the mistake of AMPS.
Sorry, what was not part of
the interior?
The interior is not.
So you might guess that the black hole interior should just be part of the black hole microstate degrees of freedom.
Mm-hmm.
Okay. But in the picture where you try to resolve the firewall paradox along these lines, what you say is maybe the black hole microstates at late times is like the first Q-trait, and the radiation is like the second and third Q-traits. Okay. And then the interior is like the logical Q-trait. So the interior is actually encoded into the radiation, not into the black hole.
I see. Okay.
And that's the massive non-locality.
I see. So the interior doesn't. I mean, I see. Okay. So the it's just wrong to talk about the interior being entangled with the radiation in a way, or modes in the.
Well, the right way to say it is that it's encoded. There is entanglement between the black hole and the radiation, but the interior is encoded into the union of the two in a way where you can access it from the radiation like this. And so you really shouldn't think about it as being part of the black hole.
Okay, but this is not a straightforward consequence of ADS-CFT, right? Because ADS-CFT is a global claim about space-time.
Yeah. No, I'm making an analogy.
Okay, got it.
Yeah. But once it's clear that you have the mathematical structure for that to work, then it's kind of very tempting to. I mean, then it's not really a clear paradox. I mean, if there's a way out, then it's not a contradiction, right? I mean. We still have to, somehow, we still have to convince ourselves that black holes take advantage of this. But I mean, that's kind of what we've been doing over the last 6 years. And it seems likely that they take advantage of this.
Yeah, but yeah, I guess one issue is that if you're thinking of black holes that are formed like physically by the collapse of stars,
Yeah.
right, then it seems a bit weird that those degrees of freedom that fall in are suddenly and instantaneously encoded as soon as the horizon is formed.
No, it's not as soon as the horizon forms. You have to wait a long time. So you have to wait for the evaporation to be more than halfway done. You have to wait until this page curve turns over and starts going down. So at early times, it is encoded in the black hole. So at early times, the black hole you're in a situation where the black hole is like the union of 1 and 2, and the radiation is like 3, so that the black hole the interior is still encoded into the black hole. But then at late times, what happens as the evaporation continues is the radiation gets bigger and the black hole gets smaller, and eventually the radiation becomes like 2 and 3, and the black hole becomes like 1.
Maybe you could draw this. This sounds very interesting and important. Maybe you could draw to help understanding the Qtrit application to black hole evaporation and the page curve. That would be really helpful for understanding.
Well, I'm trying to think if there's a picture I can draw that is helpful. I mean, somehow, yeah. I mean, I guess so. Maybe the best thing I can try to say is to draw something like. So yeah, I mean, I guess I have a. Yeah, well, I don't know if it'll help you. I mean, I can draw it like there's a wormhole that's connecting. So I can say like so at late times, so maybe like here's the black hole, and here's the radiation, which is kind of the union of these two pieces maybe. And so somehow at late times, this so the analog of these green surfaces here is something like this. Okay, and so at early times, this black hole is very big. So then these green surfaces are smaller than this. I mean, I have a paper with Engelhardt and Akers where we draw pictures like this and explain how this interior region here is like the interior. But I'm not sure. Yeah, I'm not sure that I can. Yeah, I'm not sure that I can draw a picture that will immediately make it more clear than what I have here. I mean, somehow, yeah, maybe I can try one more time, but let me see. Let's see. So I have some late time slice here, and there's there's the radiation out here, the Hawking radiation coming out. And then so this is like the logical picture. This is the picture in terms of the dot here. But then there's also a sort of microscopic picture where I just have the black hole here. It's like a dot, and then it's connected to the Hawking radiation. Yeah, I guess somehow the claim is that, so here's the radiation. So that the microscopic description is we just have the black hole interacting with the radiation. And we want to know how to think about the interior. So this black hole at late time, in the interesting situation where the page curve is decreasing, this black hole is like Qtrit 1 above, and this radiation is like Qtrits 2 and 3. And then this this region in the interior here is like the logical Qtrit there. So this is like the logical Qtrit. Maybe that's the best I can do. I'm not sure.
It certainly helps. It certainly helps.
Yeah.
So the takeaway is that the early Hawking radiation is entangled with the black hole interior, whereas the late radiation is not. And this is the way the firewall paradox is addressed. Is it the fair summary?
Well, yeah, it's somehow, no, the thing is the Hilbert spaces are different. You either talk about this picture or you talk about this picture. So yeah, I mean, the thing that makes this confusing is that the blue lines here aren't quite the same as the blue lines here. These are like a coarse grained version of the blue lines here. This is the thing that I and various people are currently fighting about, which is why I'm I haven't quite managed to enunciate it in a way that will be clear to you guys. Yeah, I think the best way to say it is just that the interior is not independent of the radiation and the black hole microstate degrees of freedom. It's encoded into the union of them, and at late times it's encoded in such a way that it lives only in the radiation. I don't think I can say it more clearly than that. Oh, who am I fighting with? Oh, I don't know, the people I always fight with, Moldesena, Meroff, Maxwell, whoever, Susskind, I mean, there's not, right, yeah. Fighting is maybe a strong word. Discussing, maybe, I don't know.
So if I'm a horizon crossing observer, right? Like, is it? So I mean, I'm on this picture after some time before I hit the singularity.
Yeah.
I just will be identical to some super complex state of the radiation, right? Like, even though it wouldn't feel like that to me, right? So is that correct?
Well, so if you're someone who's falling into the black hole, then you're kind of living in this picture, okay?
Yeah.
And so the idea is that as you pass through the horizon, the atoms, the degrees of freedom that make up your body are somehow become, in the microscopic description, they become accessible to someone who just has the early radiation.
No, but okay, but you're talking about this in this kind of accessible way, but this is an identity claim, right? You're just saying that those are those degrees of freedom, right?
Well, no, I'm kind of resisting that, because you see,
Okay.
in this picture, this red dot is really not independent from these 3 yellow dots. Okay, the 3 yellow dots are all there are. Okay, so it's not, and so the way you should think about this red dot is that it's this subspace in the Hilbert space of the 3 yellow dots.
Okay.
But it's not as simple as saying that it's just part of 1 and 2. Because if it were just part of 1 and 2, then you wouldn't be in a situation where it's not part of 2 by itself, but it is part of 2 and 3, right? That tells you that it's also somehow kind of part of 3 in some way, right? So it's more subtle than just saying it's part of 1 and 2, or part of 2 and 3, right? So that's why maybe that's why I'm saying it. I'm resisting the statement that I just literally become part of the radiation, because you could have a situation where if I only give you half the radiation, then I'm not part of that half. But if you give me half the radiation plus the black hole, then I am part of that, right? So the black hole also somehow knows a little bit about me too, through this redundancy of quantum error correction.
Yeah, but sorry, maybe I don't know. I don't want to dominate the discussion, but the black hole, you mean the stretched horizon, or the horizon, right? Not the interior.
Yeah, we can think about it. Yeah, if you want to call this the stretched horizon, I won't fight with you.
Okay.
Yeah, with the Hilbert space, whose dimensionality is e to the a over 4g.
Right. I guess I'm just like, to me, it's if I'm crossing the horizon, to me, it's just completely like ordinary, and
So that's right. And so for someone who lives in the bulk here, it just feels like ordinary bulk physics,
Right. But I was part of the bulk just a moment ago before I crossed the horizon, right? I mean,
well, you're still part of the bulk after you cross the horizon, right? I mean, the thing is, there's a duality between the bulk and the microscopic picture like this. So, in the interior is encoded non-locally in the entanglement between the radiation with itself and also with the black hole.
Okay, I'll stop here. I'm still confused, but.
Yeah, I mean, I think it's one of those things where, we can go about it with words endlessly, but the only way to understand it is to really understand the equations, and then, because you have to internalize this idea that the information is stored redundantly in the entanglement between the microscopic degrees of freedom. So it's a kind of subtle relationship. Okay, Vincenzo was asking if I can think about it as a kind of gauge symmetry. I'm not sure. I mean, I've encountered that view before. I mean, maybe in some vague sense. I mean, there was an old view where you say that the radial direction in ADS-CFT is kind of analogous to the energy scale, because things that are near the boundary are high energy and things that are near the center are low energy. And then in quantum field theory, things that are very high energy are kind of decoupled from things that are very low energy. And so that's one way to try to sort of vaguely understand this fact that this thing seems to commute with these things. So sort of prior to this work, that was kind of the words that most people would say. Yeah, I guess the problem with that though is that it's kind of not very algebraic. You know, so puzzles like this showing that this commutator is 0 and, you know, seeing, you lose this kind of redundancy when you try to think about it that way. So that is somehow less precise or less of a good picture of what's going on than what you get by thinking about, like, say, this Qtrig code.
Okay, thank you. I have other 2 questions, if there is time. I don't know. We have to continue. There is something more.
Well, so yeah, I think what I'll do is I'll skip the part about the Rutak-Yanagi formula, so you can just believe me that this holographic entropy formula I discussed last time, there's a version of it that holds in this Qtrig code. So this Qtrig code also knows about the quantum extremal surface formula. And it's not too hard. You just compute the entropy and you see that.
Okay.
But I'm happy to skip that. In fact, what I think I should do is the next thing I was going to do after this was just list a few of the consequences of this picture and then be done. So why don't you give me 5 minutes and then we can.
Okay.
Have the last 15 minutes.
Later. Thanks.
Okay. Yeah. So I'll just say, you know, you can look at the notes, but just trust me. The quantum extremal surface formula holds also in the 3Qtret model. Okay. So the model actually, you know, despite the fact that it's kind of trivial, you know, it has a lot of stuff, right? It has, radial locality, it has bulk effective field theory, you know, it has this ADS Rindler reconstruction, it has black hole microstates, it has this quantum extremal surface formula. So a lot of the kind of essentials of holography you can already understand in this model. So for me, that at least that was very useful, just to, you know, whenever you get confused about one of these things, often you can resolve your confusion by just thinking about this model. Obviously there's a lot more that you can say about this, right? You can study sort of general quantum error correcting codes, you know, try to learn what kinds of things are possible. You can make models that are more realistic, like these tensor network models. I'm not going to get into that. I just don't have time. But I did want to just describe sort of 3 of the highlights that have come out of this approach for thinking about holography. I'll just kind of list them, and then we can discuss for the remainder of our time. So the first thing is that using quantum error correction plus the quantum extremal surface formula, you can prove this entanglement wedge reconstruction conjecture, which was this idea that this rule for given a boundary spatial subregion, asking what region of the bulk you can learn about, only measuring things in that subregion, that this answer in terms of, you know, everything out to the quantum extremal surface is really the right answer. Okay. And so the proof of that is a error correcting proof. Okay. And that's interesting for many reasons, but one of them is that it kind of makes it clear that at least in some cases, the dual CFT knows what's going on behind the black hole horizon, which is something that some people were skeptical of before. You can also prove that there do not exist global symmetries on the quantum gravity side of the correspondence. Which kind of confirms an old lore, which is that in quantum gravity, there shouldn't be global symmetries. So this is an idea that goes back a long time. There were various heuristic arguments for it, but using these error correcting ideas, at least in ADS-CFT, you can give a proof of it. And in fact, assuming certain things about black hole information, you can generalize the proof to almost, to a much, beyond ADS-CFT even. And then finally, and so this is sort of something that's caused a lot of recent excitement. So using the quantum extremal surface formula, and sort of inspired by the holographic interpretation of the formula that I mentioned here, you can apply that to a non-holographic system coupled to a holographic one, coupled to a holographic system. You can derive the page curve for an evaporating black hole, and the page curve you derive is consistent with unitarity. And so it's really just using the tools that we've already been discussing. So it's not any more new tools, but it's technically more complicated because you have to use the full machinery of quantum extremal surface, and there's just no way I could explain it in a reasonable amount of time here. So at least for some evaporating black holes that you can cook up, this quantum extremal surface formula tells you that the radiation that comes out is unitary. So it's pure if the initial state is pure. So, that's further, I would say, strong evidence that holography likes option 3B among our various options that we discussed for the information problem, which is unitarity plus massive non-locality. And so hopefully this lecture has made the massive non-locality a little bit more palatable. There's much more that I could have said and didn't have time. But I think I'll stop here and then let's discuss now for the last 15 minutes. So thanks for listening.
Okay, I guess we can start the discussion time. Vincenzo is the one who has a question.
Thank you very much, Daniel, for your cycle of lectures. Was wonderful. And I have 3 questions. If you can say again very briefly how we can fix the fact that in ABS black holes do not evaporate. This is the first question. Second question, very general one. Holography between ADS and CFT has big problems that ADS is not realistic for our universe. So it is not. We can think about this duality only as a sort of a laboratory to prepare new mathematical technique for a future understanding of duality in a more realistic way. Is it the issue, the idea? And the third one, here in the final part of your presentation, you said that it is possible to build in a unitary way the page curve in an holographic system. And here you are saying that the holographic system must be ADS CFT or must be a more general kind of duality.
Yeah, okay, so let me see. So let me try to go through that in order. And I already forgot the first question. So can you just say quickly what the first question was again?
It was something that I've lost. How in ADS we can fix that?
How can the black hole evaporate?
Yes.
Yeah. So, okay. So first of all, small black holes do evaporate in ADS. But actually, the trick that's used in these recent calculations is that you take the holographic CFT and you couple it to something else. And so if the CFT is coupled to something else, then even the big black holes can evaporate. Because the energy can just leak out of the system into some reservoir. And so that's the trick which is used in the recent calculations of the page curve. So the second question was about more realistic backgrounds. Yeah. So, I mean, that's a longer term problem, especially because the backgrounds that are really realistic, you know, with positive cosmological constant and so on, are the hardest to understand in string theory. So I guess the idea is that we should at least first understand the simple ones first as best we can. And in particular, there are some similarities between the interiors of black holes and cosmological universes. And so the hope is that if we understand black holes well enough, then that will help us learn how to think about quantum gravity and cosmological situations. So that's the hope, but yeah, we're not there yet, I would say. Yeah, then about the page curve. So in some trivial sense, I mean, from the boundary point of view, the radiation will obviously be unitary, actually, in holography, because like if you just take n equals 4 super Yang-Mills and you couple it to a heat bath, I mean, there's in that description of what's going on, there's no gravity at all, right? So we know it's going to be unitary, and we know that the energy will leak out of n equals 4 and end up in a pure state in the heat bath. Okay. The new accomplishment was to give a bulk calculation that gives the same answer. And that by using this quantum extremal surface formula, right, which was a bulk formula for computing boundary von Neumann entropy. So, and so apparently that formula is very smart. It's smart enough to know that the radiation is pure. So that was the surprising thing, was that it was a bulk calculation. And in fact, people have tried to push that bulk calculation beyond ADS-CFT, because you have the formula, you can try to make sense of it. You know, even when you don't know what the holographic dual is, you can still try to use this formula and see what you get. So there's a lot of that going on these days. Okay, Siddharth?
Yeah, okay, so if I could just...
Or Vincenzo, did you have a follow-up, or you're okay?
I am only thinking. Thank you very much.
All right.
Yeah, so my question, so I'm just going to try one more time to I sort of push the point that maybe you are in fact thinking about it as identification. And perhaps, I mean, so suppose you're thinking about like the, you know, the problem that the black holes are quantum cloners, right? Like the infalling observer gets cloned in the radiation, right? If you don't have that identification between interior and the exterior, then you'll have that problem of cloning, right?
No, you don't. No. I mean, for the same reason that so we don't say that this red dot, the encoding of this red dot into the 3 yellow dots is cloning. It's not cloning. It's just it's the encoding of a quantum error correcting code.
Right, but that makes sense because they live in different, like they're sort of redescriptions of the same space, right? It's a nice, whereas here.
Yeah, but here I'm showing you two descriptions too, right? There's a description where you just have the stretched horizon and the radiation, and then there's a description where you have the space-time slice, okay? And so there's a duality between these two descriptions. And in this description, the person over here is independent of what's going on outside. But the key thing is that this description does not make sense for somebody who can do arbitrarily complicated operations on the radiation. This picture only makes sense for someone who can't do anything too complicated on the radiation. If they try to do that, then you're stuck back in this picture, and then they can see that what's going on here isn't really independent of what's going on over there.
Okay, so there's this kind of operational sort of
yeah, that's the kind of new ingredient which is I would say is sort of implicitly there here also in some way, but which we're trying to understand better here now, is that there's this restriction on what you can do in the radiation that's important, that's necessary to preserve the validity of this picture. And there's something like it here too. Basically, it's saying that I can recover from an error that affects only one of the Q-trits, but a complicated error on both of these Q-trits I can't recover from. And that's like somebody who tries to, you know, do a very complicated computation on this radiation. That's like an error that happens on both of these two, and then it breaks the code. And so when you have an error that breaks the code, then you have to go back to the microscopic picture to figure out what's really going on. And you'll see that this red dot here is really not independent of these two qubits.
Okay, so why does the complicated operation destroy that description? Is it just too complicated?
That's the massive non-locality of holography, right? I mean, that's here too, right? Like it's just that if you, so, you know, if I mean, essentially because you know, like here, if you try to do some big messy thing on both of these things, you're just going to turn this state into one of these states, okay? And then this picture of what was going on is just not going to be there anymore. You know, this picture of having this dot here just won't be there anymore. You've disrupted the emergence of space-time.
Okay, thank you.
Yeah. Enrico?
Yeah, I just wanted to clarify something. So before, when you were talking about how to solve firewalls with this, you are saying that we can take that, basically we can take the 3Q-treat space that you drawn there, and we can think of, for example, 1 as the black hole and 2 and 3 as the radiation, for example, and then we can see that we can reconstruct the interior with the radiation. So I was just interested, if we have something like that, what is the complement of that? Because in the Q-treat case, you told us that the complement is a space with a black hole in the middle. But if in this situation with the firewalls, we have, whenever we in the complement, we have the black hole in the middle, don't we just run the risk of having basically the firewall for most states outside of those with the where we have the nice bulk reconstruction procedure?
Right. So yeah, so that's one of the issues. So there's actually several versions of the firewall paradox. There's the original one in the AMPS paper, and also the work of Mathur, where they you know, where you just argue this monogamy of entanglement says that, you know, somehow this mode outside can't be entangled with the mode inside, and also the mode and the early radiation. So that one can be resolved by this kind of arguments, but then that's like, you know, in the context of special states. So there's a stronger firewall argument, which is called the typical state firewall argument, that says that even if you can fix up, you know, some state that you made by a short collapse or something like that, a generic microstate of the black hole, you won't be able to fix up. And for these kind of arguments, when the collapse is not short, I don't really know how to draw the whole space-time picture, so it's not so clear what happens. And I would say that that one is still open. So I would say the original AMPS argument by now has been refuted by massive non-locality, but the typical state one, no one has really made too much progress on it yet. We're trying. I have a paper coming out soon, but it's not going to resolve everything probably. And so that's where people get into this discussion of state dependence and whatever, which, yeah, there's a lot of confusion there. I've been trying not to unnecessarily confuse you guys by focusing on the things that I do understand.
Why do you think there's a lot of confusion on that? I mean, like if you can say maybe in a few words. I mean, I guess
typical,
a bit of an unfair question.
I mean, typical microstates are very puzzling because for one thing, a typical state should be time reversal invariant. But then for example, that means if there's a future singularity, there's probably a past singularity also. But where did that past singularity come from? Right? If you just, because you build a typical state by just collapsing, building it up very slowly by throwing stuff into the black hole. But when you think about what's going on in the interior, you just get very confused. Somehow, if you throw in this stuff slowly enough, then there's a past singularity which spontaneously materializes. Yeah. I mean, probably that's true, but I don't really know how to think about it.
Okay.
So yeah, we just don't have the tools to think about those states yet. At least not about their interiors. We can understand their exteriors, using statistical mechanics and so on, but the interior is just too puzzling.
And these would all be states basically in the complement of the code subspace.
Yeah, those are states in the complement of the code subspace.
Okay,
so, yeah, I mean, and there needs to eventually be some story about those states too, but we don't have it yet.
I see. Thanks.
Yeah, Marco.
Yeah, just maybe it's a follow-up or something. I was wondering if you can explain to me, because I didn't understand the connection of this work, I mean, code subspace and so on, to the work that Papadodimas and Raju did for solving the firewall paradox with this little hyperspace, state dependence, and so on. Because I see similarities, but I didn't really get where the subtle things are.
Yeah, well, so they were directly trying to solve this typical state firewall problem, which is a harder problem. I mean, you know, so this puzzle I had with the commutator in the center is like a very baby version of that. So there's a similarity in that both they and I like to talk about a small subspace of states. But for me, the small subspace is chosen physically, like by, for example, like the subspace where there aren't any black holes. So I think they would say that I'm solving a problem which is too easy in some sense. They really want to solve the hard problem. But you know, then the cost, of course, is that what they do is vague, and there are a lot of logical inconsistencies in it that have never been really understood very well. I mean, because they're modifying the rules of quantum mechanics, and whenever you do that, you know, you have to be very careful. It's very easy to get into trouble. So I mean, you know, it's good, it's admirable that they're trying to address the hard problem head on. But yeah, I'm really trying, at least in what I was discussing today, I'm doing something simpler and I think less controversial. I mean, everything I said is compatible with quantum mechanics.
I see. So the work is basically modifying this Born rule, right? And instead, this stuff with the Q-trit and so on is perfectly fine. I mean, we just have this massive non-locality, but it's like entanglement-like, right? It's not
yeah, that's
really
right.
screwing up things. Okay.
That's right. So I mean, so for them, the observables are nonlinear operators on the Hilbert space, which is a radical modification of quantum mechanics. So for me, everything is still linear.
These non-linear operators are in the complement Hilbert space, right?
Yeah, because they're trying
where
to
the approximation.
Yeah, I mean, they're trying to have things work on all the states at the same time, and then you run straight into all these problems with the typical states. So, I mean, I like those papers. I wrote a paper about it, you know, following up on their model. But I feel like it's an idea whose time has not yet come. You know, there are too many things we don't understand to really make sense out of that.
I see. If I may, instead, this last work about the resolution of the Paul paradox is like Pennington's and so on. There, the word code subspace is the same used here, or you have, I mean, differences also there?
Yeah, so the connection between that work and this one is still something that's kind of a work in progress. I had a paper with Chris and Netta explaining that last year, somewhat, but we were doing it in the context of a toy model that's closer to this Q-trit model. The full story is something that we're probably going to write a paper about soon, but haven't yet. But I mean, Pennington sort of, I mean, this is his bread and butter. Like he grew up doing this quantum error correction and holography, and so it's kind of a natural extension of these ideas. Yeah. But yeah, there are still several. I mean, basically, yeah, this issue about, you know, not being allowed to do things that are too complicated on the radiation is kind of the thing that we're trying to understand better. Let me also just object to the use of the word resolution of the information paradox. I don't think that's an accurate description of what happened in this paper. Yeah.
It's a specific model, right?
Maybe some journalist said that, but no responsible physicist has said that.
Okay, thank you.
Uh-huh.